start with a view of the overall functioning of a gesture control spy robot with a highlight of its special features before we get into the actual making of the robot. This project can be used as a great starting point to enter into the field of mobile robots. As you can see here, this robot comes with a small handheld device equipped with an Arduino Nano and IMU, giving you complete control of the robot. With the use of this Wi-Fi based camera module, which we have mounted on the robot, you can navigate the robot even when you're very far away using just the camera feed. Speed and direction control using the edge bridge gives precise motion even in tight spaces. RF based gesture control gives easy intuitive controls to the user. The robot also features dynamic obstacle avoidance using an ultrasonic sensor, which prevents it from damaging itself and the surroundings. These sensors, mounted on the servo motor, enables predictive knowledge of the robot's environment before the robot even actually turns in that direction. As a next step, using computer vision techniques on the camera feed, path planning algorithms along with localization techniques can make this same robot autonomous. Now let's take a look at a fun experimental video where the user drives the robot using gestures through an unknown environment with a mission to find a missing table fan and comes back to the start location. As you can see, the environment contains several obstacles, walls and tight spaces. Notice that the user is able to navigate the robot using just the camera feed. Let's now move on to installing the various components on the robot. As you can see, we already have the servo attached to the robot chassis using 2 screws and a cardboard. Let's place the various components and let's now make the servo mounting for the camera and the ultrasonic sensor.
It's a 16 buff in the dark. It's a 16 buff in the dark. It's a 16.
that we have all the components installed on the robot, let's start with what we have on the left, and we'll take you through a fun and easy way of connecting together all the components for the desired controls. To make sure we are all on the same page, we start with no prior connections. As you can see, the positive and negative from the battery is connected on the breadboard, where we'll soon be connecting the power pins from all the other components. That is the Arduino Nano, the edge bridge, servo, ultrasonic sensor and the camera, which are mounted and ready for wiring. Also, as already shown, the motor driver screw terminals are connected to the respective wheel motors. So, let's get started with a look at the connection diagram, followed by a step-by-step detailed sequence of connections.
When your time comes, don't postpone it. When others down and out, you don't condone it. Truth be told, yourself is your toughest opponent. When your moment comes, grab hold and own it. Never let go, stand tall and hold tight. Overcoming obstacles is the objective in life. Doubters all the night, and unto them you shine bright. Cause inside your head, on goes the light. Ignite. Play the intuition upon the stars in the night that glisten. To you they listen, to me you extend it a wishing. When your time comes, don't postpone it. When others down and out, you don't condone it. Truth be told, yourself is your toughest opponent. When your moment comes, grab hold and own it. When your time comes, don't postpone it. When others down and out, you don't condone it. Truth be told, yourself is your toughest opponent. When your moment comes, grab hold and own it. Never let go, stand tall and hold tight. Overcoming obstacles is the objective in life. Never let go, stand tall and hold tight. Overcoming obstacles is the objective in life.
It's a 16 buff in the dark. It's a 16 buff in the dark. It's a 16 buff.
at the connections on the handheld device that uses an IMU as the movement sensor and the RF Nano for data transmission to the robot. Here, we connect the ground and VCC of the two devices together, and the I2C communication pins, the SCL and the SDA of the IMU, is connected to the analog pins A4 and A5 respectively. We finally move on to the most important part of the video, where we upload the code to the Arduino using the Arduino IDE and understand the working of a robotic system. Before uploading the code, make sure that you select the right board and the port number. We then give read and write permissions to all the users of the port. You can then compile and upload your code. Now that we have successfully uploaded the code to a receiver Arduino Nano, we will disconnect this and connect a power bank for the Arduino to get power. As you can see, the Arduino and the edge bridge are powered up. We can now upload the code for the transmitter Arduino. To make correct use of the IMU, we first need to calibrate the zero position of the sensor. So we will click on the reset button and look at the serial monitor for calibration. As you can see, the gyro is being calibrated. So you see right now the pitch and the roll is almost at its zero position. Now when I tilt this down slightly, you will see a negative value of pitch of almost minus 27 degrees and a roll close to 5 degrees. If I put this up, you will see a pitch of positive 30 degrees. On the left, you will see a roll of minus 30 degrees, minus 50, and on the right, we see a positive roll of 50 degrees. Hence, the Arduino is able to take in the raw values of the gyroscope and the accelerometer and does its calculation to give us the filtered value of the roll and the pitch. Now, once that we have the IMU sensor calibrated, we now need to have a plan. A plan on how we wish to map the IMU motion to the direction of navigation of the robot. In our case, the IMU along with the Arduino Nano will be on a handheld device and we map its rotation to the robot rotation as follows. A negative pitch of more than 20 degrees as forward. As you can see, both the left and the right wheels are turning forward. When you bring the IMU back to the zero position, both the wheels stop. A positive pitch of more than 20 degrees as backward. A negative roll as the left rotation of the robot. A positive roll as the right rotation. So now let's see how this works. The raw IMU data is sent via the I2C bus to the Arduino Nano for filtering. Post filtering, this Arduino Nano sends the processed roll and the pitch information to the receiver RF Nano that we have mounted on the robot. This information of the roll and the pitch is used to compute the desired direction of navigation of the robot, as we just saw. We then command the left and the right wheel motors using the edge bridge. Now, before we let our robot run, we need to be careful of the fact that this is a mobile robot and we need to prevent it from running into obstacles. Hence, we have an ultrasonic sensor mounted here, which can measure the distance between itself and any obstacle in front of it. This particular sensor can detect anything between 2 cm and 400 cm. We also have a Wi-Fi based camera module here, which gives a live feed of what the robot is saying. You must have obviously noticed that the distance sensor and the camera is mounted looking front. So, how will the robot know if there is an obstacle on the left or the right before it turns in that direction? To solve this, we have a servo. If the robot wishes to turn left, we first send a signal to the servo to turn by 90 degrees. The ultrasonic sensor and the camera, which are mounted on the servo, turn with it. So, even with the robot still facing straight, we are able to perceive what the robot sees on its left. As you can see, we can take an example of an obstacle on the left of the robot. Now suppose my roll is negative. The servo moves, the distance sensor and the camera moves with it. Now the sensor is seeing an obstacle in front of it and hence the wheels are not moving. Now as soon as I remove the obstacle, you will see the wheels moving to rotate robot towards the left. The amazing part about this is that the Arduino will now make the robot wheels rotate left only if the distance sensor sees no obstacle in front of it for maybe a set desired value of say 15 cm. Once we get this clearance, the Arduino sends signals to the motor pins of the edge bridge to turn the respective wheel motors. A similar concept works when we wish to turn in the right direction. Now, for those who are interested, let's see how we read and understand the feedback of the ultrasonic sensor. So, we plug in the Arduino where we have a receiver code uploaded and check the red values on the serial monitor. As you can see, the sensor returns readings in centimeter. The value increases as I take the obstacle further apart from the robot. As I bring the obstacle nearer, the value starts decreasing. This is 2 centimeter. Hence, all we do is pick a suitable value of distance within which we wish to avoid any obstacles and use that value in the code to change the direction or stop the wheel motors based on what the robot sees. It's also good to know that the Wi-Fi based camera module hosts its data on an IP on your local network. To find this IP, we use an app called the Angry IP Scanner, which scans the activity of all IPs within any range. We start the scan, and once the scan is completed over all the IPs, we sort and then see that there are 3 IPs with a green dot, which signifies that they are actively pinging. The IP 106 seems to have a good ping time. Hence, we browse the IP address and sure enough, we see our camera settings. Clicking on Start Stream lets us view what the camera mounted on the robot is seeing. Further details of all the components used and the code will be explained in part 3 of the video.